Hey, thanks, Wes. Okay, thanks everyone, welcome. So today is rather exciting because we're going to be moving into the next session, which is going to be focusing on common safeguards. And in this module, we'll be exploring the different language between what we call safeguards and safeguarding and how that relates to the hierarchy of controls. We'll then explore some of the more common safeguards that are being used around machinery. I'll then moving on to this notion of choosing the right guard, because what we have is we actually have what's called a hierarchy of guarding with machinery safety, which is separate to WorkSafe's view of hierarchy of controls. So if we think about guarding itself, can actually be a mixture of isolation and engineering controls, and then we'll wrap that up with the management of gaps and danger zones. So bear with us as we get through that today.
Welcome to module 6.
Sorry guys, there'll be two handouts today as well. One handout is going to be around choosing the right guard, and the other handout is going to be around some of the gaps and measurements along with the slides. So hopefully those handouts will support you in going through that next process.
The standard to specify general requirements for the design and construction of The standard to specify general requirements for the design and construction of guards to provide or to protect persons from mechanical hazards is called AS/NZS 4024.1601. Describes the various types of guards, their application, and the features that should be considered as part of the design and commissioning process. For various parts of the standard as we go through module 6. In machinery safety, the terms safeguard, guard, and safeguarding are used interchangeably, but they have precise meanings in the language of machinery and equipment safety. A safeguard is the umbrella term for a number of control measures that provide workers with effective protection from harmful contact with hazardous moving parts or other unsafe conditions. Safeguards include guards themselves, safety devices, shields, and barriers. They are used on their own or in combination with others. Guards refers to a specific type of safeguard. Guards are physical barriers or covers that are designed, constructed, and installed over moving parts to prevent any contact with them by a person. Guards are the simple solution for protecting workers when access to moving parts such as belts and drivetrains is not required during operation. Guards are reliable, cost-effective, and low maintenance when properly designed and installed. Devices include a number of alternatives to guards, such as interlocks, two-ender controls, and pressure sensing devices such as light curtains and pressure sensitive mats. These solutions are more technical than a guard, but may be the only solution when access to hazardous areas is required during normal operations, such as when feeding materials into a machine for processing, and a guard would interfere with this task. Safeguarding devices should not be a default in terms of replacing a guard. You must explore how you can use other types of safeguards first. Guards are the first choice of control to keep workers from coming into contact with hazardous moving parts or to contain harmful fluids and projectiles, particularly when access is not normally required during operation. Sometimes it is necessary to move a guard aside so a worker can access a point of operation during normal production work. If so, the guard should be interlocked to stop the machine and any hazardous movement of the equipment until the guard is put back in place and the safety control system is reset. Where access to the danger zone is not required during operation, a fixed guard shall be used. In other circumstances, guards need to be adjustable to allow materials of varying thickness to be fed into a machine. Typical types of guards include fixed, distance, movable, adjustable, interlocked, or self-closing. It's important to note that guards must prevent access to the hazardous area from all directions. Guards must not create additional pinch points or other hazards. Guards must safely contain broken parts such as belts and chains, and guards must allow for the safe lubrication and minor adjustment without guard removal. When applying guards, you need to check they offer good visibility to feed points, stand up to normal wear and tear, meet normal production and quality needs, and are difficult to modify or defeat by humans. In determining what type of guard to use, this should be considered as part of a risk assessment. And the most important selection criteria around that risk assessment process is understanding the probability and foreseeable severity of any injury, the intended use of the machine, the hazards present at the machine, and the nature and frequency of access by people in the modes including pre-start, operational, post-operational, maintenance and cleaning. It would be appropriate to use a combination of different types of guards. For example, if a machine has several danger zones and access is required to one of them during the operational phase, the guards can consist of a fixed guard combined with an interlocking movable guard. In a similar way, a combination of safeguarding devices and guards can sometimes be required. The standard reference in this module is very useful in determining what type of guard to choose. In this module, we have included an attachment in this webinar called a safeguard table. It explores the types of safeguard, their typical applications, the action of the safeguard, and the advantages and limitations that the safeguards offer. Please make use of this type of material because it gives you some really good examples of real-life applications. Fixed guards and distant guards are guards which are physical barriers, and they keep people out of danger zones or danger areas during normal use, maintenance or cleaning. But all these guards need to prevent workers from reaching through, reaching over, reaching under, and reaching around the guard or the structure and coming into contact with the danger points. In the case of distance guards, these should be at least 1.6 meters tall and at least 900 millimeters away from the danger zone. They can be further or higher if there is a projectile hazard. If that distance or fence guard is between 1 meter and 1.6 meter tall, it must be at least 1.5 meters away from the danger zone. Distance or fence guards above 2.7 meters do not allow a worker to reach over. No distance or fence guard should be less than 1 meter high, as they could allow a worker to topple or fall into the danger zone. You must also consider the height from the floor surface to the structure and the distance to the danger zone to determine what body part can enter from under. The distance from the floor surface to the structure should be less than 180 millimeters to prevent a whole body entry. Fixed guards where used should safely contain any broken parts and allow for any safe lubrication or other minor adjustments without the removal of the guard itself. Adjustable and movable guards are made up of a fixed guard with adjustable elements that are moved to suit each task. They can be self-adjusting, for example guards that are forced open by the entry of work, or barriers that can be moved to a safe distance from the danger zone. Removable guards are guards that can be removed through the use of a special key or a special tool. Typically, these types of guards would have a secondary safeguarding device such as an interlock. And these interlock guards then work by cutting power to the machine when the guard is opened. They are a good guard to use when a machine needs to be accessed often. Choosing the right guard is important. I've attached one page of the standard called Annex A, which is the guidelines to assist in the protection of guards against hazards generated by moving parts. I'd like to explore that a little bit more in detail, so I'm going to split the diagram into two parts and we're going to zoom in. So in part one of the flowchart, obviously the assumption here is that using guard is only required because there are hazards that are present. So if hazards are present and access is required during use, then you move on to determine about can access the danger zone be totally prohibited. If access is not required during use, then your default must be a fixed guard. If access can't be totally prohibited, then you must look at self-closing guards and adjustable guards. If access to the danger zone can be prohibited, then you can move on to part two of the flowchart. If access is required for setting, process correction or maintenance, and that access is only once per shift, then you can use a movable guard with an interlocking device, or without guard locking, or a fixed guard. If access is required during the working cycle and does open the guard cause no hazard to cease before access, then you can use a movable guard with interlocking device with guard locking. You can see here what they're trying to attempt. They're trying to basically say that a fixed guard prevents the worker from accessing the danger zone to begin with. And if we can't then prevent that access to the danger zone, then we need to minimize the access at all times. And if they do have to access the danger zone, then we need to de-energize the source of the hazard at its point, so a worker is no longer exposed to the hazard at that time. Let's now explore some common safeguarding devices. Let's start with an interlock. Where an operator can remove a guard or open a panel, gate or fence and enter a danger zone, the interlock will de-energize the machine's control system. The interlock ensures the machine will not operate if the guard or the gate is in the open position. Resetting whatever has activated a safety device, for example, closing a machine guard that has a safety interlock, should not start the machine function. The machine function should only be restarted at the designated control panel. Two-handed controls or hold-run controls require the operator to remove his or her hands or entire body from the hazardous area or the danger zone before the machine can be cycled. So on these examples, the two-handed controls in figure A requires both hands to depress the buttons at the same time. The controls are spaced apart so that one hand can't operate both controls. They are designed of a particular type which requires the buttons to be pressed in so that people can't try and tape down buttons or activate them in other ways. Work in a similar fashion in that the person has to activate both levers at the same time, typically in separate rotations, and if the lever was to be released, it will move back to the stop position automatically. Presence sensing devices stop the machine if the operator or another worker enters the hazardous area or danger zone while the machine is cycling. Presence sensing devices such as light curtains, photoelectric devices, and pressure sensitive mats function this way. The effectiveness of these devices depends on the time and distance required for the worker to reach the danger zone before the hazard has been eliminated. It means that you have to calculate the time that it takes for the source of the hazard to be de-energized. Once you understand the time that it takes, then you can position the light curtain the distance from the danger zone by using effectively a speed which is often based on walking speed. That means that an operator, when they break the beam before they reach the danger zone, the source of the hazard has already been de-energized and therefore eliminated. Emergency stops. This is the involuntary tripping or activation of an emergency stop device if all or part of a worker's body approaches or enters the hazardous area or danger zone of machines. Examples include an e-stop button on a control button or near the worker or the danger zone, an emergency contact bar in front of the in-running feed rolls, or an emergency tripwire installed along a conveyor system. You need to make sure that emergency stops are prominent and clearly and durably marked. Typically, e-stops are red with some type of yellow button. That the e-stops or emergency stops are immediately accessible to each user of the machine, have red handles, lines, bars or push buttons, and labelling can also be used, and are not affected by electrical or electronic circuit failure. Any emergency stop should not be used as part of a machine process. If a process stop is required, this should be a separate and clearly marked and identified for that purpose. Guards are there for the management of gaps and distance danger zones. Materials used for constructing guards generally can consist of wire or expanded or perforated metal. Mesh or grid guards may be installed to prevent workers from reaching through the openings and contacting the point of operation. This is done by placing the guard at a safe distance from the hazardous moving parts. The effectiveness of a guard opening can be judged by a reach test carried out, of course, with machinery locked out and safely at rest. AS/NZS 4024 has a series of standards to determine this gap in reach. On the screen are displayed those standards. In a later slide, we've tried to make life a little bit easier by looking at what we call worst case or worst credible types of gaps and distances to give you some insight to what these standards are trying to achieve. The distance a person can reach sets the minimum height for some guards or the minimum distance of barriers from the hazard. Reach is limited by the length of arms, fingers, hands, legs and feet. Once you understand what the gap is and you can understand what body part can enter, you can then consider issues around reaching up, reaching over, reaching around, reaching through and reaching under. By understanding the gap and the distance to the danger zone, we can then determine what body part can enter. For example, a gap of say 6 mil to less than 20 mil allows a finger or a toe to enter. The distance to the danger zone for the finger needs to be more than 20 millimeters. Otherwise, the person's finger can come into contact with the danger zone. Further examples could be, if the gap, say for instance, is about 20 mil, that would allow a hand to enter. Therefore, the gap from the entry to the danger zone needs to be no less than 120 millimeters. These numbers I'm providing are very much dependent on the shape of the gap, depending whether it is a slot shape, a square shape, or a round shape. The numbers provided, being say 20 millimeters for a hand, is the conservative value that is taken regardless of the shape size. For instance, if it was a slot, that slot may well prevent the thumb from entering, which means that the distance to the danger zone could be less. Another example, if the gap is say about 120 mil, that allows an arm to enter. Therefore, if the whole length of the arm could enter, that means that the distance from the gap to the danger zone needs to be no less than 850 mils. Typically, the distance from a person standing on a floor surface and reaching up, that the distance from the floor to the hazard should not be less than 2.7 meters in height. And as discussed earlier, if the gap is more than 120 to 180 millimeters, that could well allow a body entry. I recently had an example on a machine where they had installed light curtains. The gap from the light curtain to the outside wall was approximately 200 millimeters. This allowed a person to squeeze between the wall and the light curtain, bypassing the light curtain and therefore no longer becoming effective. I've also seen examples of light curtains where a person is able to reach over the top of the light curtain and come into contact with the danger zone, or go under the light curtain and come up into the danger zone as well.
So that wraps up today's module. And as you've seen, guys, this is really the technical component of machinery safety, and it's not for everyone's appetite or cup of tea. There is no expectation that health and safety practitioners need to be involved in the design of a guard. The design of a guard should be undertaken by an engineer. I think what's useful is that safety practitioners understand how workers can access danger zones, how those gaps around machines, or those gaps around fences, or those gaps around things like light curtains, which I see a lot of, that we need to think about the ergonomics of the body. We need to think about how people can reach under, reach through, reach over, or reach around. And to me, that's where I see a lot of the failures, that how the guard or the fence was originally designed, there's been some process change and people can now access those danger zones. Just because it's been guarded then doesn't mean that it's guarded now. So any questions before we wrap up from the team today?
Let me quickly open up for some live questions and answers. 1 sec.
Good afternoon. How are you today?
Hi, Rangi, how are we?
Good, good. I've got a few questions. One of them's around light curtains. So we recently had one of our existing or old bin tips peer reviewed, and one of the things that they found was that the light curtain doesn't meet the performance level required. So how is that something that we can pick up from site, or is that something that needs to be determined through a safety requirement review by an SME?
Look, it's an interesting question because I think there's two things. One, you could measure the distance from the light curtain to the danger zone.
Okay.
So that you can do a distance measurement, which is great. You can also do the calculation that when the light curtain is broken, how long does it take for the energy to be removed? And there is a table that I can send to you that then tells you what that distance should be.
So did you say time taken to
To
de-energize?
remove energy, correct.
Okay.
So you can imagine that the way it's been designed is that a person walking through the light curtain should not be able to access the danger zone in that time frame.
Okay.
So the standards haven't changed. What's more likely is either the light curtain has been moved over time, or the amount of time it takes to remove energy has changed.
Okay, that's interesting.
To me, it would be a change management problem.
Yeah.
Not the standard changing.
Yeah.
However, I always say to people, light curtains are the last line of defense. Why couldn't we have chosen other types of guarding, such as self-closing, adjustable?
Yeah. And
So
in this
your
case,
case,
it's the bin tip in feed.
that's correct.
Yeah.
Yep. So I guarantee you the light curtain has been moved.
Okay. That's and that leads into my next question around light curtain distances from the floor. Is that in one of the standards that you showed earlier? I think it was 1701, 1702, 1703, 1704, 1801.
Yeah, they are. Yeah, they are. So the common thing, I see a lot of light curtains where there's quite a big gap. And the point here is this notion of what we call reasonable foreseeable misuse. So if someone could actually go under or reach an arm or a leg into the danger zone, it doesn't matter why they'd do it. But if they can do that and come into the danger zone, then the light curtain is not doing its job.
Is the distance, gaps in reach distance, do they differ between light curtains and between like fixed guarding?
No. Although many engineers install a light curtain with a lot of height from the ground up. The issue here is they've done the light curtain to the danger zone, but there may be other things that are moving that the person can come into contact with.
Oh, okay. Okay, so sorry.
Yeah, so how the light curtain was designed and what other danger zones could be present could be different.
Okay.
So I see that quite a bit with like a pallet wrapper, that the base of the thing is actually moving and you could get an arm and to come into contact with it.
Right.
But what they designed the light curtain for was actually someone reaching into another part of it.
I see. So just as an example, the light curtain placement from the floor should be less than 180, or unless you can reach in underneath and reach a moving part, so then it would be less than 120.
That is correct. Yeah.
Okay, thank you.
Or you move the light curtain further away. So either extend the light curtain or move it away. So the greater distance you're away, the less you can reach in.
Yeah, okay, so that makes sense. It's quite similar to the
like a
physical
fence.
guarding. Yeah.
It really is. Yeah.
Sorry, another question. E-stops. The length of the E-cord. So you've seen one of our graders where it's 40, 30 meters.
Yeah.
Does the standard, I had a look in the standard, but I couldn't find a golden rule with the length required. or an ideal length. Is there a golden number that we shouldn't exceed?
So what they're saying there is obviously that the pull cord can't go around corners. It's got to go in a straight line.
Mm-hmm.
And it needs to have supports over a certain distance to stop, you know, the pull cord from dropping.
Yes. Yep.
But what's relevant with a pull cord is how much force it takes to activate.
Yep.
So if I recall, it's trying to remember how many, so it's 70 Newton meters. So was it 7 kilos of force?
Yeah.
So if you go along that pull cord and it doesn't activate in under 7 kilos, then it's a problem.
Okay. Okay, cool. I just wanted to
And
confirm that.
you fix the problem by either putting in more interlocks, like shortening the distance between more interlocks.
The actuator.
Yeah, the actuators.
Yep.
That's their job.
Yep.
So at any point, if it's 40 meters, anywhere over that 40 meters, if it can't activate and under 7 kilos of force being applied, then it's not doing its job.
Thank you. That's definitely cleared that one up.
Right.
Okay, I've got one last question. Sorry for taking all the airtime. Okay, interlock doors. So you talked about interlock doors and how they de-energize equipment. So we have had in one of our new bin tips that has been relocated from one site to another, they've upgraded with interlock doors, which is awesome. And one of the questions that they asked was, okay, so it de-energizes equipment. Is this an acceptable substitute for lockout tagout?
The answer is there any other stored energy?
Yes. Okay. So yes,
Okay.
for it'll be pneumatic.
Yeah. So if there's pneumatic, lockout tagout would not even address that.
Yeah, true.
Okay. So the whole idea is lockout tagout is sorry, go back to it. If it's routine access, more than once per shift, you should be using an interlock, not lockout tagout.
Yeah. For cleaning and maintenance?
How often are they cleaning?
Oh, it'd be each break, so twice a shift.
Yeah, then we should really be looking to use interlocks where we can.
Okay, so they would be an acceptable form of
based on frequency of use.
Okay.
Because I would argue a lockout tagout requires human behaviour.
Yes.
To fit the padlock to remove energy.
Yeah.
An interlock requires the action of a human to open a gate.
Okay.
That machine can't be restarted until the gate is shut and the control panel is reactivated.
Okay.
If people are that worried, you can use a lanyard interlock where there's actually the lanyard or the key has to be removed so that the person's, got that with them.
Okay.
Meaning the gate can't be shut and no one can restart it.
Yep, without that lanyard.
Yeah.
Oh, brilliant.
Okay, the only thing about lockout tagout, the only thing that saves someone is a padlock. That's why they have to have single keys.
Cool. No, thank you very much.
Thank you. All right, Wes, I know we're running a bit over time and I know you got other things to do. So guys, feel free to share any comments later on, and we can even do a wrap up in the next session as well, where we explore the risk assessment model.
Yeah, guys, if you've got a question for Brent, shoot me an email and I can pass it on to him and he'll be able to answer them. Unfortunately, I am pressed for time today, as I've got a workshop starting in a couple of minutes. So I do thank you for coming along today, guys. I really appreciate it. And I'll make sure that this webinar is uploaded by the end of this week at our YouTube channel, where you can revisit today's webinar to see if you've got missed maybe something. And please make sure that you can share them with anyone else that wants to get more information regarding machine guarding, etc. We are here to share. We are here to learn together. We are here to help each organization keep their workers safe and well. Thank you again, Brent, for your time. Thank you guys for coming along. I do appreciate you all. Until I see you next time. Cheers.
Thanks, guys. Bye.